expect 4 lines, right? 3 by 2, na? The other isotope having I equal to 3 by 2. So 4 lines, we got it rather in a distinct fashion in the previous molecule. Here, instead of getting 4 lines, one could see 2 lines. This is 1 line, this is 1 line, somewhere here. Yeah, this is 1 line. Third and fourth could not be seen in under X band condition, but who knows? There is no data available for the Q band of this compound. So could be, if you go for Q band, you might have seen the other 2 lines. But the point of concern is, even you don't get the full thing, but the impression is very clear. Impression very clearly suggests that the other isotope is also being operational as far as the overall ESR is concerned, but in a restrictive fashion, that because of the fact of the things have gone beyond the experimental magnetic window, which is very restrictive for X-band condition. So if you go for the higher machine, where the magnetic window would be spreaded further, and you could expect to have the additional 2 lines. And if you blow it, if you blow this one, okay, it's nothing visible actually. Okay, but if you blow it, you will see these 2 areas essentially look like the central one. Okay, and there you could also see the lines. Again, the argument is there is no chromium chloride interactions, and that's because of the fact of lengthening of that bond beyond the boundary conditions. Well, now it's a very simple case, like the vanadium case. Now, if you have manganese compound, particularly low spin manganese 2. So low spin manganese 2 means what is manganese? D5S2. That means D5, and you have 1 unpaired electron, T2G5. But if you take high spin configuration, then 5 unpaired 2. So your S equal to 5 by 2. And that's much more complex situation. So we are not talking about any complex situation right now. We're only talking about the most simple situation that S equal to half, as it is being shown over. So low spin. Okay. Now your manganese, it is known already from the literature that I equal to 5 by 2 and 100% abundance. So no way to miss it, like copper, like your vanadium. And it is octahedral compound. Okay, and as we know, all of you must be knowing by now that if you have all the ligands around the metal atoms, particularly if they are monodentate, and all the ligands are identical in an octahedral environment, then you should expect to have very symmetric or ideal or close to ideal octahedral situation with the angle 90 degree, whatever it is, 180, etc., etc. And that means the distortion is essentially very minimum at the molecular level. So X, Y, and G axis, they are essentially identical, right? You cannot figure it out even from the bond unless there is your John-Taylor distortion. That is present in the copper case. We know that John-Taylor distortion is dominating if you have unpaired spin in the EG orbital, not in the T2G orbital. T2G orbital, you may have a very weak John-Taylor distortion, right? So you can have, if you have this compound, one could anticipate that you'll have a rather symmetric environment without much distortion, etc. That means the bond distances, that means manganese oxygen distance along X, Y, and G axis, they would be almost identical or very close to each other. And that is being reflected in the spectrum, and no G parallel, G perpendicular, A parallel, A perpendicular, nothing is there. But if you go to the same situation, I will talk about a little bit later on, the copper situation, or in a chromium situation if you go. Okay, copper situation if you go, your D9 configuration, right? So you will have 1 unpaired electron into your T2 EG level. Okay. And if you have one unpaired letter, there are 3 electrons. So out of 2 Eg levels, one would have 2 and other would have 1. The question is the 1 electron would be in which orbital? G square or x square minus y square? And we know the J down, J in, all sort of consideration. And if you record the crystal structure of copper hexa co-molecule, you will see the 4 distance copper oxygen distances in the plane, they are identical. But the other 2 oxygen, along the g-axis, they are identical but different than the xy plane copper oxygen distances. That means 2 set of distances you will be getting. 4 they would be identical and 2 would be identical, but those 2 would be either smaller or greater than the other 4 set. And that means you will have your distortion along the g-axis. Okay, and that would be reflected in the EPR profile. So before going, let's see the copper is there. Copper will come. So before that, this is one example that proves EPR could be also nasty. Nasty in the sense where things are not as clean as one could anticipate or expect, right? For example, this enzyme, if you look at that cobalt is there, and naturally you could see that cobalt is linked to one X equal to halide, let us consider, or cyanide, whatever you consider. So cobalt is in the +2 state, right? So if cobalt is the +2 state, because one anion is here, one anion is here, neutral compound, +2 state, and cobalt +2, that means D7 case. Now D7 case, if you have high spin situation, then your spectrum would be very complicated. We'll discuss it later. But if you consider low spin situation, that means T2G6, Eg1. It will be very simple compound. Okay. Now, like nickel 3 compound. Okay. So it will be rather simple. But the I value is 7/2, and which is, I think, close to 100% abundance. So you will not miss it. But the problem is, if you record the EPR of this molecule, what do you see it that, if you look at this molecule, it is octahedral molecule, and along the g-axis or one of the axes, I do not know which one would be x, which one would be y, which one would be z in the bulk. If you have the single crystal, then you can fix the axis, right? If you have the bulk, either solid or solution, it will be random. So you do not know what which corresponds to what. But the fact is, essentially, you are getting axial type of spectrum. I have not talked about axial, rhombic, etc., which we will talk later on. But accept me the fact, axial means x equal to y and z equal to not xy. That means x equal to y, not equal to z. Okay, that is bond distances or geometry along the x and y are mostly identical, not the z one. And here you see that you should expect to have the at least 7 lines plus these 4 nitrogens are there. Though they are different, but that different cannot be highlighted too much over here. So the 4 nitrogen means 9 lines. So first is 7 line and then 9 lines. So essentially, if you have one isotropic signal, that would be split